Hello, in this lecture we will start studying about the analysis procedure for trusses. And there are actually two analysis methods, and we will now start discussing about the method of joints. In this method, as its name implies already, we were analyzing the equilibrium of joints in a truss, and we will do this sequentially, meaning we will analyze joint by joint, one after each other, after we complete the analysis of the entire truss. Now, in the two-dimensional trusses that we study, three-dimensional trusses are not included in this course, the joints are or behave like particles, as we discussed in the previous lecture. So therefore, for studying the equilibrium of particles, we have to write two equations of equilibrium for each and every joint. And in order to do that, to explain the method, I'm going to use an example, a practical example. So I'm going to start with a Warren truss, a simple Warren truss, like so. And the internal members are also sloped, diagonal members. So this is our truss that we will analyze using the method of joints, simply supported by a pin at A and by a roller at G. Now the truss has two forces acting at C and E externally. So these are the forces applied on a truss, having each a magnitude of 10 kilonewtons. And the standard dimension of the truss panels is 3 meters. So 3 horizontal panels of 3 meters, and the height of the truss is also 3 meters. What we need to do, what we are asked to do in this question, is to calculate the forces in all the members of the truss. And we will do this by following a number of steps. So step by steps in order to understand the method very clearly. The first thing we need to do, obviously, is to determine all the forces that act on a truss. So we know the applied forces. We still need to determine the forces corresponding to the supports, the reaction forces. So we need to know all the forces that act externally on the truss. I'm making a small comment here that this is not needed for cantilever trusses, but we will see that later. We will see why is that later. So to determine the external reactions of the truss, we will select the whole truss as our body to analyze. So we don't really care what's happening inside the truss. We are assuming the whole truss as a rigid body, as we've already done so far with many other bodies. These are the forces, internal and external, that act on a truss. The external ones after we removed the pin support at A and the roller at G. And of course we write three equations of equilibrium. If we sum the forces on the horizontal direction, there are no forces applied in that direction, so the horizontal reaction at A is 0. Then if we sum the moments at joint A, at point A, equals 0, then that will solve for GY. It will cancel AY, that goes through A. So therefore GY will be equal to 10 kilonewtons going upwards. And if we do the same at G, summing the moments at G, that will cancel GY, and we can quickly solve for the reaction force, the vertical reaction force at A, AY. Now in this case, this was a simple truss, which was symmetric, so both the forces and the geometry of the truss were symmetric. So when both of these conditions are satisfied, the forces acting on the truss are also symmetric, as you can see, 10 and 10. Now, very, very importantly, at this point you must do a check to ensure that your reaction forces that you've calculated are correct. And we can do this by summing the force on the vertical direction equal to 0. It's very important to do that, because if your reaction forces are incorrect at this point, everything else will be incorrect. And that's not a good thing to happen. Now, step number 2, we were going to analyze the first joint as a particle. We need to look for a joint where we already know a force, so a force that is given, and also we need to select a joint that has no more than 2 unknowns. So, because we can only solve for 2 unknowns when we write the equilibrium equations for a particle. So therefore, can we start with joint B? No, because joint B has no known force applied to it, so we have no number to start with. Well, can we start maybe with joint C? Because here we have a force of 10 kilonewtons. Well, not really, because then we have 1, 2, 3, 4, AC, BC, CD, and CE, the members with unknown forces. But we can start from the left end with a joint at A, where we have a 10 kilonewton force that we know, and we have 2 members with unknown forces, which are AB and AC. So I've started already drawing the free body diagram of the joint at A. The 10 kilonewton force is given. FAB and FAC are unknown forces, shown in green. If we sum the forces on the y direction, FAC has only x components. So we can quickly solve for FAB by knowing the angle theta, which we can easily determine from the overall geometry of the truss. And therefore, FAB will be equal to 10 kilonewtons divided by cos theta, 3 meters divided by 3.35 meters. This is the length of member AB. And therefore, this member will be equal to 11.118 kilonewtons, the force in the member. Now, we made a guess originally. We draw the arrow of FAB pushing into the joint. So therefore, the member is in compression. Second equation, summation of forces in the x direction equals to 0. And from this one, we will solve from FAC. Sine theta will be, in this case, half of the panel length, 1.5 meters, divided by 3.35 meters. And the result will be 5 kilonewtons, positive, so meaning that our original assumption, our original direction of FAC was correct, and this was pulling away from the joint, so FAC member AC is in tension. Now in step 3 we go to the next joint with 2 unknowns, and that would be joint B, because in this case the 2 unknowns will be the forces in members BD and BC. Note that we cannot go to joint C and analyze joint C, because joint C still has 3 unknown member forces, CD, CB, and CE. So, as we said, we're going to analyze joint B. Again, we must draw the free body diagram of joint B, in which we already now know the force in member AB, which is 11.18 kilonewtons in compression. So it's pushing into this joint, right? It's pushing into both joints at the ends of the member. So pushing into the joint at A and pushing in joint at B. And I'm assuming that FBD is also in compression and FBC is in tension. Just a guess. If the results of the equation of equilibrium lead to negative results, then means that our original assumptions were wrong. So if we calculate the numbers, the force in member BC will result as being equal also to 11.18 kilonewtons in tension. Our assumption was correct. If we sum now the forces in the horizontal direction, so now we have all 3 forces being part of the equation. In the end, FBD will also result as positive 10 kilonewtons. So our assumption that the member FBC's intention was correct. So the force in member BC will be equal to 10 kilonewtons in compression. So what do we do next? Well, we go to the next joint in sequence, the next joint that has no more than 2 unknown member forces, and obviously now this would be joint C, because joint C has now, we know the force in member AC, and we know the force in member BC. We need to solve for the force in member CD and the force in member CE. Same procedure. We draw the free body diagram of joint C. The forces in blue are the ones that we know now, FBC and FAC, both of them in tension, pulling away from the joint. I'm assuming that FCD will be a compressive force and FCE a tension force. Don't forget about the system of coherent axes. And again, we can sum the forces on the y direction to eliminate FCE, which has only an x component. And you can easily see, even from the symmetry of this joint, that FCD will result as 0 kilonewtons, 0 force. Some of the forces on the x direction now. Remember that when we write the equation of equilibrium here, I'm going to write this term anyway, negative FCD sine theta, but FCD is 0 as we determined in the previous equation. And therefore from this expression we can determine the magnitude of FCE, which is 10 kilonewtons, positive number. Our guess was correct, so the member FCE is in tension with a magnitude of 10 kilonewtons. And then step 5, 6, and so forth, in which we will continue joint by joint. So maybe next will be joint D, and then E, and then F, until all the joints in the truss have been analyzed and we have determined all the members, all the forces in the members of the truss. So we're now at the end and we have to present our results. This is very important, the way we present our results, because for somebody checking or verifying or looking for the results of your work, it will be very difficult to go through pages of calculations and free body diagrams of many joints and looking for the actual results, even if you have, highlighted them. So what we must do is draw a schematic of the joints of the truss, as you can see here, show the external forces acting on the truss, so the applied forces as well as the reaction forces acting on a truss. And then we draw the member forces that we've calculated. I will draw the members in tension in green and the members in compression in purple, just for the purpose of differentiation these. But what is very important is the directions of the arrows of the forces in the members. And remember, we always show forces acting on the joints. So forces pulling away from the joints indicate members in tension, and now forces pushing into the joints indicate members in compression. And when you've done this procedure with all forces, internal forces in the members of a truss, then this will represent the final answer. Now anybody looking at this diagram would quickly see and determine the forces in the truss. Now, when you've analyzed joints sequentially, So you've done joint D, joint E, and joint F. At this point, you would know all the forces in the members of a truss. However, there's one last step, one last joint, joint G. But now you know all the forces, but you should perform a check at the last joint. Very important to make sure that the last joint is also in equilibrium. So the forces in the X and Y directions summed up add up to 0, meaning that your calculations were correct. The reason for that is that, as you can imagine, because we're going sequentially, joint by joint, a simple mistake done somewhere along the calculations will actually propagate to the end, and you'll have everything wrong from the point where we've made that mistake. Very, very, very important, crucial, in fact, to do this check at the end. So please never skip this step at the end. Now, in summary, before we end this lecture, I would like to tell you the advantages and the disadvantages of this method. So, good things, it's a method that is very simple to use because we only use 4 summation equations for particles, so 2 equations for each particle, easy. Secondly, because we go joint by joint sequentially, in the end we will end up solving for all member forces, which is good when we need to know that. For example, when we design or analyze the entire truss. The bad, it's tedious because you have to do the analysis of many joints, step by step, same type of operations, kind of boring, but in the end you solve for everything. And the second more dangerous thing that I mentioned is the propagation of errors, which is dangerous. You have to be cautious, and you should always, as I mentioned, always perform the check at the end by ensuring that the last joint is in equilibrium. And that is a confirmation that your calculations have been correct. Now, this is all about the method of joints. As you can see, it's a simple method. It's good. It solves for all the members in a truss. And I would like to now thank you for having attended this lecture. And in the next one, we're going to look at some specific conditions with regard to trusses.